Today we will discuss the energy approach in simple harmonic motion. Sometimes in this a particular area of physics, that is simple harmonic motion, or more broadly oscillations, we face some problems where it might become apparently a bit difficult to figure out the forces and solve the problem using the conventional uh, the so-called force method. Sometimes it might become difficult to use the force method to solve that problem. So we can use an easier method called the energy method to solve problems of simple harmonic motion. To illustrate this, I've taken a problem from Principles of Physics by Halliday, Resnick and Walker, and so I found out that this particular problem, it's problem 100 of the oscillations chapter from that book. So I can use this problem to show you how we can apply the energy approach in SHM, simple harmonic motion. But before I dive into this problem, I need to illustrate how we use, or what is this energy method and how we use it in problems by using that simple harmonic oscillator. That simple mass attached to a spring, and that is kept on a frictionless surface. So we'll consider that system first. And in that simple harmonic oscillator, I'll show how we apply that energy method. So let us first draw that system. Let's say this is a rigid wall, and here I have a spring and a mass block is kept on a smooth frictionless surface. Say the mass is m, the spring constant is k. So I pull this block a bit and displace it, some x displacement, so it will oscillate. Let's say some velocity v. With this velocity it moves towards the right side. Now I can describe this system in terms of the various forces acting on that mass, but I'm using a different method. It is called the energy method. So we basically talk about the energy, the various forms of energy involved in such a system, right? So we have a mass block which is oscillating, so it is having some velocity, so it must possess some kinetic energy due to its velocity, due to its motion. And if it stretches the spring, then the spring will store some elastic potential energy. So we have to know what are the different energies involved in this simple mass spring system. We have two forms of energy in this particular system: kinetic and potential energy. The kinetic energy of the mass m and the potential energy of that spring, which gets stored in that spring when the mass is oscillating, when it stretches the spring or compresses the spring. So in those situations. But see, in SHM, in this particular case, in SHM there are no dissipative forces for this oscillation. So the total energy oscillates between this translational kinetic energy of the block and the potential energy of the spring. In other words, the total energy is constant, which means there is no change in the total energy of this system. So in other words, I can say the rate of change of energy with respect to time is 0. There is no change in energy. That is when the energy remains constant, right? Now, total energy of this system is constant. So what is the total energy? Let us write the total energy of this mass and spring system. See, the block is moving with some velocity v, it is oscillating, and there is some stretching and compression in the spring. So we can write the total energy E as the kinetic energy of the mass block plus the elastic potential energy which gets stored in the spring every time it gets stretched or compressed, let's say by some amount x. So that elastic potential energy is half kx square. So now if we differentiate this E with respect to time, what do we get? Let's do that differentiation. I mean, if we do this, what we get? Let's check it out. So we are getting dE by dt as 0. This is what we already know, which implies now here we have half mv square. So if we differentiate v with respect to time, we are getting half m 2v dv by dt. That is what we get, plus half kx square. We differentiate that with respect to time, so we get half into k 2x and time derivative of that position x, that displacement x. So this equals 0. I mean, this is what we get. This is the equation. I hope you can see it. So now see, in this equation, this particular term, sorry, I need to increase this thing's length, I guess, and yeah, so see, this particular term is dv by dt. So we can write it as second order derivative of displacement with respect to time, and this term, look at this term. So this is dx by dt. We can write it as velocity. Why? Because velocity is rate of change of displacement with respect to time. Oh, I forgot the 2 here. Yeah. And dv by dt. V is dx by dt. So dv by dt is d2x by dt2. That is acceleration. So I write this equation in that form. That is half m 2v d2x by dt2 plus half k 2x times v, that equals 0. This is the equation. Have a look. Now we solve this. The 2 cancels. What do we get? M v d2, I'll write it like this. I think I need to increase the thickness again. Yeah, d2x by dt2, this equals minus kxv. This is what we get. If we solve this thing, we get this. Now this v gets cancelled and we get d2x by dt2, that equals minus, see how I'm writing it, k by m, I've associated them in a bracket, times x. What does this mean? This is of that form minus omega square x, which you get from your force equations in SHM, force method. This is what you get. d2x by dt2, the acceleration, minus k by mx, which is of this form, minus omega square x. This is that what we have compared. In other words, we've got omega. How much is omega? It's square root of k by m. Hence, for this particular mass spring system, our time period is 2 pi by omega. That's what is the time period in SHM. So that is 2 pi square root of m by k. And if you remember, you get this very result from your force method. So this is the energy method of solving in SHM. We took this mass spring system. We found out the time period of oscillation of this mass block of mass m using energy method. The mass here is m. So this is the energy method. See what we did. Energy of SHM is constant, which means change in energy is 0. Total energy here oscillates between these two terms, the kinetic energy and the potential energy, which means that the rate of change of energy is 0, dE by dt is 0. So we wrote the derivatives of E with respect to time, and we have substituted these two parts, as you can see, and then we got our omega. We compared the coefficient of x, so we get omega square as k by m. So omega is square root of k by m. So the time period of oscillation is 2 pi by omega. That's 2 pi square root of m by k. And hence we have got the time period of oscillation of this mass block system. Now let's come back to our original problem. We will use this same method to solve this Resnick-Halliday problem. I think I need to copy this thing. Okay, yeah, I need to copy this thing and I need to paste this somewhere down, because here the space is occupied. Somewhere here, yeah. I'll paste the problem, I'll enlarge it. Yeah, so this is our problem. So basically this is our problem. Yeah, so let's read the problem. I hope it's visible. So in this figure 1557, a solid cylinder of some mass capital M is attached to a horizontal spring. The stiffness constant is 3 Newton per meter. It rolls without slipping along a horizontal surface. If the system is released from rest when the spring is stretched by so many meters, find the translational kinetic energy, the rotational kinetic energy of the cylinder as it passes through the equilibrium position. Show that under these conditions, the cylinder's center of mass executes SHM with period t given so much. So you have to prove that. And how do we do this problem? Okay. So the potential energy about the turning point is equal to the total kinetic energy. As I said, that the total energy of this particular system is constant. So which means that we can write the potential energy as half this is our potential energy, half kx square. See, for this system it is equal to the total kinetic energy. Now since the cylinder is rolling without slipping, so which means there is some rotational as well as translational kinetic energy. These two constitute the total kinetic energy of this cylinder when it is in motion, and that equals the elastic potential energy of that spring. That is what we are doing here. So we write first the kinetic energy due to translation, half m v square, plus the rotational kinetic energy, half ICM. ICM means the moment of inertia about center of mass. This is the expression, the energy expression. So here we know that for a disk, for this disk, okay, I'll draw it. This is our V, right? And it is rotating like this with some omega. The radius of this disk is r. So we know that omega is equal to V by r, and we can write V as first order derivative of x, which is x dot, and acceleration as x double dot, second order derivative of displacement. X means the displacement when the disk rolls, right? When it rolls, and there is this spring attached, spring constant k, right? So this is the diagram, and here we have our ICM. This is the center of mass. So ICM is what? ICM is equal to mr square by 2. That is the moment of inertia about center of mass for a disk. So we write this value in this equation here. So we get, what do we get? Half kx square. I'm doing the algebra. So V denotes here the velocity of center of mass. Omega square. Okay, wait. Omega square means this thing, V square by R square. You'll get to know why I am expressing the energy terms in terms of M and V. See, M and V. Maybe there's an R, but everything is in M and V. So what are we getting? If we simplify this, we get, now observe that before I proceed further, that this is our translational kinetic energy, and this is our rotational kinetic energy. That is what I want to say. Now I proceed. That is, if I simplify this, how much are we getting? We are getting something like this, half kx square equals half mv square plus the r's cancel, basically mv square by 4. So we can write half kx square as 3 by 4 mv square. Now look into this relation very carefully. So it is evident that, let us go back to the first part of the problem. See, it is evident that using that boxed result, that result in the box, we can find the translational kinetic energy, the rotational kinetic energy of the cylinder as it passes through the equilibrium position. This is easy, right? This translational kinetic energy, the rotational kinetic energy of the cylinder when it passes through the equilibrium position. How? Like this. If we know the relation between kx and m and v, so basically we can substitute the values. See, what are we given in the problem? We are given the value of stiffness constant as this much and the value of x, it is stretched by this much. So what does that mean? Our k is 3 Newton per meter and x is 0.250 meter. If you have k and x, so for part A of the problem, I am not plugging in the values, I am telling how to do it, the approach. What you do is that you use this relation. We can use this relation, right? To find the translational kinetic energy, which is half mv square. This is the translational kinetic energy. What is it? Well, mv square, from this equation, mv square is how much? It is 2 by 3 kx square. That is what you are getting. So half mv square is how much? Kx square. So basically kx square by 3. So here you just plug the value of k, plug the value of x, and then you get the value of your translational kinetic energy, right? For rotational kinetic energy, that is the part B of the problem, what do we have to find out? Half ICM omega square, right? That is mv square by 4. This is the rotational kinetic energy. Half ICM omega square means half mv square by 4. So mv square by 4 in terms of k and x, how much? It is kx square by 6. I hope you get it. We are getting it from this equation, right? See, mv square by 4. So I place the 3 here, I transpose it, so I get kx square by 6. You plug in the values of k and x, you get the rotational kinetic energy as well. This is how we do the problem, how we solve the problem. Now coming to the final part C of the problem, which I'll solve obviously, because that is what I wanted to show, how we use the energy method to find out time period in SHM instead of using the conventional force method. Here the total energy of this system is same. Let us go back to that diagram. See, diagrams are very important in physics. Here, as you can see, this thing, this cylinder rotates about this point P, this yellow marked point P, right? Why I said that? Because when we are finding our total energy, basically we are finding moment of inertia about P, right? If we do so, we get the total energy indirectly. I mean the total kinetic energy. Now the total energy of this cylinder spring system is what? The kinetic energy plus the elastic potential energy which gets stored in the spring. The elastic potential energy is half kx square. The kinetic energy is what we were doing here. We did it a few minutes ago. Now this is the part C, where I can show you that how we use the energy method to solve these SHM problems. The total energy is the total energy is half kx square plus, now I am writing the total kinetic energy. The total kinetic energy means the rotational kinetic energy plus the translational kinetic energy, right, which is 3 by 4 m v square. This is the total C. We get this from this result, right? Look at this result very carefully. This expression is the total kinetic energy. This expression is the total potential energy. So if we add them, we get the total kinetic energy. So basically this result in the box is super important for the problem here. If we add these two terms, we get the total energy. That is what I have written. Now the energy method says that, as we did for that block system, this is 0. This is what the energy method says. So we are doing the time derivative of these two terms. What is the time derivative of this term? What is the time derivative? half k 2xv, as we did in that mass block also. I'm writing it. See, sorry, what's the time derivative in this case? Let's figure that out. See, I'm writing the RHS first, that is 0 equals, now the LHS, dE by dt, half k 2 times x, and then that dx by dt. I'll get that dx by dt. See, from here, half k x square 2x dx by dt, that is v, dx by dt is v, plus 3 by 4 mv square. So m 2v dv by dt, that is d2x by dt2. This is what I get. So I'll prove how I'll get the time period. I'm proving that expression of time period. So if I rearrange this equation, this one, I get d2x by dt2 equals minus, this is what you'll get if you rearrange the terms and do the algebra basically. This is what you'll get, right? d2x by dt2 is minus 2k by m x. Now what does that mean? This is again coming in that form, minus omega square x, right? Which means this is omega square. This is what I am talking about. The acceleration is minus omega square x. So how much is omega? Omega is square root of 2k by 3m, and we know time period is 2 pi by omega. So the time period becomes how much? Time period becomes t equals 2 pi square root of 3m by 2k, and hence we have proved that the center of mass of this cylinder we had here is executing simple harmonic motion. Show that under these conditions, that last part, the cylinder COM executes simple harmonic motion with this much period. This was the time period. This is what we are getting. If you check, this is what we are getting. This is our final expression. This one. This is what you are getting. And why this is a SHM? Can you figure that out? Why is this motion an SHM? We did all the way, we solved the problem, we assumed the motion to be SHM, but why? Why is it SHM? Like if I ask you why is it SHM, as see in this question, they have said, show that under these conditions the cylinder COM executes SHM. Why? I leave that part to you, and perhaps you'll comment me, why do you think that cylinder is executing SHM at all in the first place? I've solved the problem. I've assumed that it is in SHM, but why do you think it is SHM? Why? What is that simple thing which indicates that this is in SHM? Well, this is pretty easy, super simple. This is a kind of an easy peasy thing at the end of Mahabharata. All of you know. Well, I'm waiting for the comments. Why do you think this cylinder executes SHM? And what has that got to do with the time period expression which we have got in this final? Hoping for some constructive interaction in the comments. Thank you.